Well, it cannot order of, yeah, so it is log n basically, omega log n, okay. So it is at least log n. Why is it at least log n? Kravchenko's theorem talks about the size. Well, that is one way to argue. So that is what is a more simpler explanation, much simpler. Let's say you don't use any theorem. So again, it is just pigeonhole principle that, well, if you have a exactly. So if you have a circuit whose depth is less than log n, which has bounded fan in, then it must skip some input. It cannot depend on all inputs if its depth is, let's say, small o of log n, right. So its depth must be log n, at least log n, so that it looks at all the inputs. And the parity function or the XOR function, it actually must look at all the inputs, because even if you skip one, I mean, even if you skip one bit of the input, the parity function can depend on that bit. So we know this. Okay. So what we have is that D of XOR is at least log n by this argument. Okay. So now what we have is that we have that the communication complexity of XOR is also this. So we kind of have connection in one direction. So what we will show is that not only does the communication complexity, well, yeah, it doesn't say. So this says it is at most log n, but well, it can be even smaller than log n. I mean, we still don't know whether this is a tight upper bound or not. What we will show next in the remaining part of this lecture is that this upper bound is actually tight. You cannot have communication complexity protocol which is smaller than log n. In fact, we will show the following general result. That so this is due to Karchmer and Wigderson, and I think this was 1980 probably. Yeah, 88. Okay. So for, let f be a Boolean function, then what we have is that the communication complexity of the relation corresponding to f is equal to the depth of the smallest circuit that computes it. Okay. So this gives a tight bound on the, well, whichever way you want to look at it. So suppose if I want to consider depth of circuit, so one way of studying depth is via the communication problem, the corresponding communication protocol. Okay. So how do we prove this theorem? So the proof is actually not very difficult. So, and as expected, it goes in two ways. So first we show that, well, given a circuit, okay, there is a communication protocol corresponding to that circuit which has the same, I mean, whose the number of bits communicated is corresponds to the depth of that circuit, and the reverse. So given a protocol, there is a corresponding circuit. Okay. So first, let us prove the direction that okay, given a circuit, there is a communication protocol. So C R of f is at most D of f. So let C be a circuit computing F, and using De Morgan's theorem we will assume the following. So assume that C does not have any NOT gates and all literals are at the leaf level. Okay, so well, if you have a NOT gate in an intermediate level, what we do is we apply De Morgan's and we keep on pushing it down, and then finally when we reach the very lowest level, we just replace the corresponding NOT gate with the, I mean, with the corresponding variable or its complement, whatever it is. Okay. So now we will show that, yeah, we'll show that there is a communication protocol for R of F, which communicates at most the depth of C many bits. Okay. So what is the idea? What is the idea of this problem? So the idea is as follows. So, well, what does Alice and Bob have? So we are looking at the relation R of F. So Alice has an input X which evaluates to 0. Bob has an input Y which evaluates to 1, right? Now they have to communicate among themselves and they have to produce, well, an index on which X and Y differ. So the idea of the protocol is that Alice and Bob, they would in some sense agree on a path, okay, from the root all the way up to a literal, such that on that particular literal X and Y differ. Okay. So Alice and Bob traverse along a path from root to a leaf of C such that at the leaf X and Y differ. Moreover, so that is one thing. Moreover, it is not just any path, but it is a path which maintains this invariant. Okay. The path also maintains the invariant that Cv of x should not be equal to Cv of y for each node V in the path. Okay. So before giving you the proof, actually it is easier to give the intuition. So suppose I have a circuit. Okay, I start at the root. What do I know at the root by my input? So what I know is that, well, okay, so what we have is, so Alice has, so let's write A. So Alice has X and Bob has Y. What else do we know? We know that f of x is what? F of x is 0 and f of y is 1. Which means that C of x must be 0 and C of x must be 1. So the invariant is satisfied at the root. So at the root, I have the property that, so here I have the property that C of, well, x is, it is little more than saying not equal to. I have the property that C of x is equal to 0 and C of y is equal to 1. And let's say I'll use the notation subscript to denote that which node I am looking at. Okay. So CR of x is 0 means that at the root they evaluate to 0. So this is what is given to us. Now I have to find a path. Okay. So Alice and Bob have to agree on a path. Now let's say that from here there is, so both these nodes have 2 children. Okay. Now if x and y disagree at the root, then what we have is that there must be one node, okay, there must be one child again on which x and y must disagree, and that would depend on what? That would depend on what kind of a gate R is, whether it is an AND gate or whether it is a OR gate. Okay, what do I have? So let's assume without loss of generality it's an AND gate. So suppose if R is an AND gate, what can I say about x and y? So CR of x is 0. If R is an AND gate, what does it say about the inputs to an AND gate which output 0? It can be anything. It can be that both are 0 or it can be one is 0, 1. What can we say about Y if R is an AND gate? Huh? If R is an AND gate, then for Y we can say something a little more stronger. Then what we must have is that both of these must be 1. Okay. Now what Alice does is, so suppose if R is an AND gate, then Alice would decide, well, which of these two is evaluating to 1. Okay. So Alice decides which of these two evaluates to 1, and then Alice would choose which node to go to. Okay, or well, not 1, which of these two evaluates to 0, because I have to maintain the invariant that C at the next level also they must be 0, and well, let's call them as, let's say, VL and VR. So let's say that they go to VL, then it must be the case that CVL of x is 0 and CVL of y is 1. So if R is an AND gate, then it is clear that CVL of y is also 1 and CVR of y is also 1. But which of the two is 0 would make, I mean, would determine Alice whether Alice would want to go left or right, and that is what Alice would communicate to Bob. And this is the entire idea of the proof. Okay. Because CR of x is 0. It is meaning that on input x, what does C output, or the gate R output? So R is the root gate. So on input x, what does the circuit output? Because the circuit computes F, then on input x, it must output what F is. Okay. So this is just, I'm just overloading the definition because I would like to use not just the output of a circuit, but the output at gates as well. That is why this subscript denotes the output of a circuit at a particular gate. So if again, so if it is a, if R is a OR gate, then it is just a symmetric argument. Okay, so if R is an OR gate, then what we have is that, well, if CR of x is 0, then both CVL of x must be 0 and CVR of x must be 0. Okay, so Alice doesn't have anything. Alice can go to either one. Okay, but then Bob has to decide which side Bob wants to go to. Okay, so if CR of y is 1, it means that at least one of them has to be 1. So then Bob decides whether to go to VL or VR depending on which side is 1. Okay, and that is essentially the protocol. So let me write the protocol. Okay. Or so let me just correct this a little bit, because the invariant that we maintain is, well, this is true, this is of course not false, but we actually maintain something stronger. So not just we maintain that CV of x is not equal to CV of y, what we maintain is that at every node of the path, CV of x is equal to 0 and CV of y is equal to 1 for each node v in the path. Okay, that is what. So it is true at the root, and then we'll show it is true at every intermediate node as well. So start at the root. So suppose, let me show this pictorially, this is easier. So suppose I have a node V with children VL and VR. Okay, so if V is a AND gate, then Alice sends 0 if CVL of x is equal to 0, and Alice sends 1 otherwise. Correspondingly, if V is a OR gate, Alice doesn't do anything, then Bob sends 0 if CVL of y is 1 and Bob sends 1 otherwise. Okay. Okay. So note we are doing exactly the same. So if V is an AND gate, then Bob doesn't has to decide. Alice basically decides which direction to go to. Okay, so Alice sending 0 means that Alice is telling that, okay, go left now. And because at the left node, at the left child, that invariant is maintained. And if, well, the invariant is maintained at the right, then Alice sends 1. And Bob basically does the same thing. So V is an OR gate, then Bob will maintain the invariant that Bob sends 0 if, well, the invariant is maintained at the left node, and Bob sends 1 otherwise. Now, what do you do at the next step or at the next round? So, if the bit sent is 0, then what do? If Alice or Bob send 0, then continue at VL, else at VR. So which direction you go to is determined by what bit is sent. Okay. Now it is let's and when do you stop? So you stop when, as I said, you have reached a leap. So stop when a leaf is reached at this point. We have by the induction hypothesis, we have a literal on which x and y differ.